Muthukumaran. It has been a fantastic conference. It's a good beginning. I hope that the keynote speakers are available. I would like to call upon the first speaker, Professor Kenichi Soga, University of California, Berkeley. And I know that it's 10, 10:15 here, little late here, 10 minutes in the night, but then he has been, in fact, I met him yesterday in his office, and I hope he's available, and then I can request him to start his lecture. And Professor Kenichi Soga,
hey,
is he available?
how are you?
You're able to see him? Okay,
Yeah.
Great. Okay, yeah, just let me introduce you. And of course, I should say a few words. I think Professor Kenichi Soga is, he's from the University of Kyoto, and he worked he got his PhD from University in Berkeley, and then he did a lot of, he was also in Cambridge University, and he did fantastic work. Actually, it is, in fact, he was telling me that it will be a new defining role in geotechnical engineering. What he's going to, I have seen the lab and all that. Professor Kenichi Soga, it's yours. You have full time of allotted time, so kindly go ahead. Thank you.
Yeah, thank you very much, Professor Sivakumar Babu. It's great to see you again.
Yeah, thank you.
Yeah, so I'm going to share my screen. Do you see my screen?
Yeah.
Yeah, okay. Well, first of all, I would like to thank the organizer for having me for this particular interesting conference that you're running at the moment. It's a totally different time zone, and I hope everything will be okay. I'll do my best. So the title of my presentation is Distributed Sensing and Monitoring of Geotechnical Structures. And before I do that, I'd like to thank all my researchers in our group who's looking at sensing and modeling of infrastructure. And these are the people who really do the work and then produce the results. So many of the things I'm going to show you today really come from them. So I have to acknowledge them, and they're the workforce that we have at UC Berkeley. Also, we have a lot of collaboration and funding agency to support our research coming from infrastructure owners that you can see over here, to civil engineering industry and technology providers, because we are trying to bring the emerging technologies into geotechnical market. We have a lot of collaboration with the research organization, not at least, but funding agency, starting from National Science Foundation, California Energy Commission, and Department of Transport, and etc. So I really thank for the support. Just to show the excitement. So excitement we have in geotechnical engineering, these are emergent technologies coming up, and I'm sure many of you have used them perhaps, and then enjoying using it, try to see the value for geotechnical engineering. Computer vision, LiDAR, UAVs you see over here are the system that use the vision or sort of point clouds to get the movements, and we start to see them used as a movement devices. So you can go to like cameras, you can go down to 0.1 millimeter precision if you start to have a very high resolution cameras that you see over here. Or people use infrared cameras to look at sort of a moisture and that sort of thing. So you can see the vision is really transforming our geotechnical structures. You see LiDAR, so people start using LiDARs to look at comparison of the movements. Now you start to see satellites. So many people start to use satellites because they become autonomous. They will keep on recording your movements without asking you to do so. So this is a really exciting area, but they go around 10 to 20 millimeter precision. One thing I want to focus today is on distributed fiber optic sensing, and it's really a sensor made of fiber optics, which can be embedded for lifelong monitoring, which I'll discuss later on. But again, the precision is about 1 microstrain or something like that. That is like, if you have a 1 meter gauge length, it's 1 micro movements. So that's really small movements. And finally, wireless sensor network is the area that see a lot of things happening already in the market. It allows continuous monitoring at difficult to access sites. And these are the sort of products that we came out from our research organization. The challenge actually is the difference in time scale. We tend to design our infrastructure for 100 years, or maybe you want to last our infrastructure more than 100 years. But then actual demand, for example, what you see in certain towns that you live, may be quite different 40 years ago. That's quite true on the Bay Area over here, or even in London or other major cities. 40 years ago is quite different from now. And I'm sure that 40 years from now will be totally different. So the demand changes more rapidly. With climate change, that becomes more of an issue as well. So how can we make our infrastructure more adaptive to change? If you want to make it adaptive to change, you need to embed intelligence into your system. And the intelligence may be sensor or data analytics, but then many of the technology we do is very short-lived technology. And so the question is, what kind of technology is available to prolong that particular lifetime? So infrastructure is fixed in space for a long time, but then that's because of a long time, it makes them critical because the demand changes. So we may need to think about 100 years design life to be more adaptive to change. And if you believe in that, then you have to put intelligence into your system. A wireless sensor network has been a big sort of an interest to many of us. And as you can see from here, you see that technology, this is when I was at Cambridge, we built it, and 10 years ago, this was that. And then within 3 years, it comes like that, it's spin out, and then it's part of a Leica system now. And then you see other companies, like this is the wireless sensor company based in Cambridge, and then Atterbury is London. But again, these are wireless sensor network system. And you can see the speed that it's only 6 years that changed to this level, and then another 6 years it going to the market. So the speed is very, very fast. And nowadays, and I'm sure you can get these in India as well, in terms of you have a variety of sensor system that we use in practice that can be used in wireless mode. That means that you can attach these to a difficult access site. And so you can have a camera mode or vibrating wire string. These are conventional sensors attached to these wireless sensor systems. One of the big things that happened more recently in the past 5 years ago is the traveling distance. So what happened is that this particular wireless sensor mode, you can have one as a gateway, here's another one, here's another one. The data recorded from 5 can hop to come to your sort of an internet network. And now you can see that this is going like 2 kilometers or 3 kilometers hopping to get the data. And these are called mesh network. And these are common in our field. And that allows us for geotechnical monitoring to be more realistic because you can hop for long distance, for large, long distance measurements. Obviously, the challenge is about the use of batteries. So if you have a low sampling date rate, which is like measuring temperature, humidity, light, or orientation, maybe you just need one hourly data. So if you look at, say, tilt mode with a certain battery, something like this, and if you do hourly monitoring and the mesh network, like what we see over here, it sort of hops together, theoretically, this can last for 10 to 15 years if you have a good battery to start with. Now, once you have a high sampling data rate, like acceleration or wind velocity or sound, then you need to have a little bit more careful in terms of how you do your power management. A vibration sensor may require 300 hertz, or acoustic noise sensor may require 2 kilohertz. If you say you take 5 seconds selected recording, so that means that takes, if you do 5 seconds of this noise, then it takes 1 to 2 minutes to send the data because there are a lot of information in that particular noise or acoustic sense data. If you do that every hour, because the data is so much, it only lasts for 40 days. So you need to be a little bit more clever in terms of how you scavenge the energy to make this wireless system go for a long time. For example, you can have a trigger load that you don't record all the time. You just trigger it when it's necessary. Or you can use energy harvesting like this one is that uses vibration energy to scavenge the the energy from the environment and then use that to send the signals. So exciting time for us. Now, distributed fiber optic sensing is one of these main topics that we work at Berkeley and also in the previously. This gives you what we call continuous strain temperature vibration profile along the fiber optics. So this is a standard optical fiber that you see over here used for telecommunication. For telecommunication, light with a digital signal converted to light goes through, and you go to the other side, and then you convert it back to digital signal. And that's what sort of an internet fiber optic communication is about. But the light goes through, but as you see, this is made of glass. So as you go through, every point along the fiber, because it's not perfect, there's some inhomogeneity, and that allows us to light to reflect, come back, and that's called backscatter light. So when you shoot a light, every point along the fiber, you get a backscatter light. And you know, let's say you shoot a light and then it takes delta t to come back from this one, you know where it came from because it's delta t times speed of light divided by 2 with some coefficient will give you that location. So you can do that for every point along the fiber. That gives you a distributed nature of the physical quantity you're measuring over here. And then what you do is that when you get your light, you look at the signals. When you look at the signal that's coming back in the frequency content, there's 3 important what we call scattering signals. And we use these scattering to convert it to strain, temperature, or vibration. So most of the common one is brilliant for strain. This brilliant is same as your vibrating wire strain gauges. If there's a strain at that particular location of the light coming back, if you look at the frequency, this particular peak shifts when your strain is great. And that gives you, if you convert this frequency shift, you can get your strain. Or equally, you can get your temperature if there's no strain transfer. There's another technique called distributed temperature sensing, which you look at this particular scattering, and then this amplitude change is related to temperature only. And this is related to molecular vibration of the sort of a crystal at that particular location. There's another one, which is Rayleigh scattering, which is also related to amplitude change, and that gives you temperature, strain, and vibration. And this is called distributed acoustic vibration sensing, DAS or DVS. So today I'm focused on strain because many of us are interested in strain. You can now purchase variety of sensor fiber optics now, and they are sort of made to be very robust. So for example, if you have a fiber which is very, very fragile, it's maybe as less than 10 microns, but they're coated around very like metal reinforcer or other material to protect. But the point is that when you step on it, that strain transfer goes through this diet of layers into the fiber, and the strain outside is same as your strain inside, and you convert that to convert it to light signals. You can have a temperature measurement. In that particular case, when you step on it, you don't want to have a strain transfer. But then if this fiber is floating inside the gel, then the change in temperature will be reflected over here. Meaning that the strain cable has 2 components, which is often the case, strain and temperature. So you need to have one cable to do temperature compensation to get your strain for typical any sensors that you have, which is temperature sensitive. Sometimes you can get some cable like this, which you have inner part will have a fiber floating inside the gel to give you the temperature, but then the other one is tightly buffered to transfer the strain. And that gives you, one cable will give you 2 things, but then it becomes more expensive and a little bit more difficult to handle. So at UC Berkeley, we've been trying this to a variety of problems like pipeline monitoring for the water and gas. This is the foundation, which I'll talk about later on. This is a building foundation movements on the roads. I'll show you this later on in terms of how the construction sort of heavy equipment is transferring the load into the ground for stability of these construction machines. And I'll show you this later on in terms of sort of an embankment settlement monitoring. We put this in oil and gas application to look at the oil and gas well performance. You can put it in the tunnel lighting, spray concrete lining to look at the, in this case, cross passage opening. This is a river cutoff wall. You can put the cables. In this case, we were looking at the bending of this particular wall, and similar to the slurry wall or diaphragm walls. Perhaps you can put it on the ground to look at the ground movements. This is a project that I'm involved with the Singapore government of the new 51-kilometer deep tunnel sewage system, where they're putting a fiber optics for all the sections, and that will be worth of 200 kilometers of cables. Again, tunnels, ground anchors, and then pavement and that sort of thing, which I'll show you some of them later on. This is one of the projects. This was in London. This is the earlier study that we did. This is the old masonry tunnel affected by the new tunnel construction going underneath in King's Cross area that you may know. You may be over there. And this particular site at King's Cross, there's some, you can see the blue one, which is over here, is a water canal. And the retaining wall of the water canal is attached to the, we don't know why, but on this particular masonry wall. So you can see when the excavation is done over here, this particular tunnel gets distorted. And then there's some sort of a disruption in terms of the other neighboring infrastructure. So we attach the optical fiber around the tunnel, like these 5 different cross sections, and then 3 longitudinal direction. But the point is that this becomes one line, and it goes to the interrogator to measure strain at all over the places and give you the distributed strain along here. So you can see the fiber optics over here. It's the early days, so we went to DIY shop and bought this hook, and then we attached the hook, and then we put the cables around, and then pre-tension it, and then glue it so that we can measure tension and compression as a change in strain. Now, if you have this particular tall tunnel, when the new tunnel is right underneath, it gets vertically elongated. That means that this particular tunnel will squat or sort of elongate in this particular direction. And therefore, if you put your fiber optics around, you get 2 tension at 2 sides and then compression over here. So if you look at it, the data will move from tension, maximum tension, going down to 0 and going to the compression side, and then go back to tension, which you'll see over here, going to tension, going to compression at the crown, and going to tension on the other side of the wall. And this is something we want to see. This particular tunnel was going diagonally underneath. So sometimes your tunnel is over here, or sometimes your tunnel over here, and that particular peak that shifts along like this. So this is a conceptual diagram that we have. So this particular work, you can see that the fiber optics will attach at 5 different cross sections, 5 to 2 represent over here. And here's from the one side of the wall to the crown to the other side of the wall. And this is 0.1% and 0.2%. And as the tunneling machine goes over here, you start to see these different sort of changes responding to it. So the tunnel machine goes over here, and then it just passed the 522. And when you see the 522, you can see tension over here, compression, and then tension over here. And the reason why you have more tension over here is that it's on this side of your tunnel. Let's go to 520. 520, it just passed, and you can see more here because it's underneath. If you look at 518, you see this particular butterfly shape that I showed you earlier. And 516 is the other side, so you can see the larger tension on this particular side. And it goes 0.1 and 0.2%. I'm going to show you again, just to start looking a little bit more carefully again, passing 522, 520. And what I want you to look at is 516. So 516, the tunneling machine is approaching, it goes up as it passes, and when it passes, it goes down. As we know, the most critical time is when the tunneling is right underneath, and that's when the machine or the tunnel get distorted the most. So you can start putting these on your pile. So this is your pile, and then you can put the fiber optics inside the pile while you're pouring your concrete to create a pile. So you can see this is a cage, and the cage is attached to these fiber optic cables. And as the cage goes down, cable just rolls in, and then these construction workers just clip the cable, and then you pre-tension it at the top and you pour your concrete. And what you want to see is something like a load displacement, but then in this case, this is the increase in load or change in load with time as you put the load. And what you see is that as you increase the load, there'll be the largest strain at the top, and then the strain will decrease. And that's what you want to see. And as you increase the load, the strain at the top will be larger and then decreases. And that's what you're going to see over here. Top is 0 on the surface, and the bottom is 30 meters deep. And you'll see that as you increase the load, you start to see an increase in load coming over here. And then you see the distributed strain coming over here, and the gradient is related to your shaft friction. And as you can see, the load increases, you start to see a little bit of interesting feature coming up, which is a little bit odd, but then these are the localization happening, which may be related to some local effects of your pile. This is where you had a little bit of change in geometry of your pile, and that's what you see over here. So you can start to see the actual performance of these piles when you look at these data sets. Here's another work that we did. In this particular case, it's what we call post-gradient technique to improve the the base resistance or base stiffness. And I'm not going to show you the details over here, what we did, but while we do post-grouting, we can see how the strains are developing underneath. But let's say we finish that, and then you apply a load from the top to see how the strain is distributed inside this particular pile. So in this particular case, we had 4 different cables around the pile, and then we have 3 strain gauges at different depths. And so the black line is the average of the 4 cables, and you can see that top has a larger strain, decreases because of the shaft friction, and then you have some compression at the bottom related to the end resistance of the pile. The triangles are the average of the strain gauges, and then they look nicely, and this is what you expect. However, if you start looking at the individual data, so these are individual data that you see from the sort of a vibrating wire strain gauge, and you start to see, oh, what is this particular data set? And you may say, I don't like this data set. However, if you plot your fiber optic data, the purple one actually goes like this and goes like this and comes over here, where the opposite one goes like this and goes like this and comes over here. And actually this particular data set that you got from the vibrating strain gauge is actually real in terms of measurement, because actually the pile is bending even though you apply your vertical load. So that's the actual performance of this particular pile as you apply your load. And you can see that the bending flips at the other side. And if you look at the other direction, also there's a small interesting behavior of the pile. And we did 3 different tests on different piles, and we did the same thing, but again, you can see the variation in the bending depending on different ways of doing the sort of grouting at the bottom. But then the point is this is the actual behavior of the piles. But once you get your strain, you can sort of integrate to get your displacement, and then you can get your shaft friction by looking at gradient. And that's what you want to look at, is the shaft friction versus the movement. And you can get what we call a TZ relationship or TZ relationship as well. And you can read this particular paper to derive this data set from this particular data set of fiber optics to get your shaft friction with displacement. At the same time, when you just pour your concrete, the concrete starts to cure, and that will generate a lot of heat, and then temperature in the concrete will rise. And you can monitor that using fiber optics. So you can see that the temperature rise with time. This is 20 hours one day. And then you can see that the blue and green are heating more than the other side of the pile. And that flips on this particular one. So we have about 1,000 points per line. So there's a 4,000 data sets of this temperature rise and going down with time. So this is like for a given depth, I have 4 different cables, so I get this temperature, but you can see that different location hydrates or it rises in temperature in a different way. And what you can do is that you can do some simple one-dimensional axisymmetric analysis of the heat transfer from your pile into the soil. And then what you can do is that you can start by saying, okay, you have a heat model, a generation model, which is given in the concrete literature, and then trying to see how heat dissipates or temperature dissipates into the ground. And your fiber optics is right close to the interface between the pile and the soil. And we have that for 4 different locations. So for example, you get your data like this from your blue line, from your fiber optics data, and then you do the analysis. But what you do is that you vary this interface radius and then trying to match the data. And then you say at this location, your pile radius is that particular one. And you can do that for 4,000 data sets. And that allows you to get this particle sort of pile shape. And then you can compare this with your loading performance. And indeed, you see a better grip or better shaft development over along here, which is in sandy formation. But in here, you can see a little bit of necking. And this is where we saw it's in the clay silty formation. But then here, it's initially slips, and then it starts to engage some shaft friction. And you can start to get, these are what we call thermal integrity tests. And we start to see this in the market, but this is something that you can start to use using this fiber optic sensing. So isn't it nice if you can measure, put this fiber for whole life management? You look at construction quality control, and then you can look at the real behavior, and then you can do future proofing. You can do this for sort of grout, grouted anchors, and see how the sort of a skin friction is, shaft friction, bonded strength is developing at this particular one. So you can see this in a similar way. Here's one project where we have this sort of a big sort of a machinery trying to pull. And then because in San Francisco, we have a very soft ground, what are the platform needed and what kind of strain is developing inside? And what you can do is that what we did is that we attached the sort of inserted the fiber underneath, and then there's some number of fibers going underneath and becomes an in situ extensometer. And then what happened is this sort of a machinery goes in, and then you can start to measure what kind of strain is developing inside that particular ground, in the soft part of the ground and then hard part of the ground. And then when you apply your loading, in this case, pulling over here, this particular machining will change its sort of a loading profile, and that start to give you a larger increase in the low strain and that sort of thing. So you can see how the ground is performing by this interaction of the construction machinery. You can do this for attaching after you do your cone penetration test. Before you do the grout of that particular hole, you just while you're doing your grouting, just push in your sacrificial cone with the fiber optics and then grout it to create an in situ extensometer. So then you get your strain profile, which you can integrate one to get your displacement, and that's what you see over here. So you can see that cone truck is pushing, but after you do your cone penetration test, you do this another cone, but with a sacrificial with the cable in it, and you create what we call in situ extensometer. So this is a Treasure Island in our Bay Area, and then they're doing a fill to do some settlement measurements of this particular site. So this part you see on the right is your cone result. So you can see that the cone resistance goes like this and then decreases over here, which is your soft part of your formation, and goes up again over here. And then this is your tip resistance, and this is silly friction. Now, when you apply your load, you start to see a strain developing. So you can see over here, and what you can see is here corresponds well to over here, which you're giving a soft layer of that particular one. But there's another one over here, you're giving a large strain development, implying there's a soft part over here locally, and that corresponds to this particular point. So it starts to give you interesting information about which mechanically behaving, this is cone resistance, but how they link to actual behavior of the embankment settlement. And you can also do the integration of the strain, assuming the bottom is not moving, and you can get your vertical strain profile, and then you can compare the settlement at the top of the surface with your sort of surface measurements. And that is done over here, where you see that the fiber optic settlement is giving you in the blue, and then the yellow one is our survey settlement. And the jump over here is because they had to change the surveying target because it had to do. And so we just honor that. So you can see that the trend is very similar before the moving and before the after. This is artificial. This should be continuous to here, but you can see that they show us similar movements. At the same time, we can use this to measure the vibration. That means that if you do the geophysics, you can also measure and then do the VS measurement, and you can have to do some similar little bit of analysis. But then what you can do is that you can drive your shear wave velocity measurements using just a cable that you already installed, and use what we call distributed acoustic sensing that measure the vibration. And that links to the soft part of the ground. Now you can start to do that by sort of embedding these in a trench, and then you see the cable embedded in trench, and you can do a geophysics, And in this case, we're trying to get the P-wave where the groundwater table is from this cable and using this particular technique. Or you can get your VS profile using this particular technique. There's a little bit of analysis that you can do, but you can use it as a geophysical method. And this is called distributed acoustic sensing that measures the vibration. So you can see that we start to put these like in the pavement, and then you put on the pavement, and then you see that cable is embedded in the pavement. And then what you can do is that you can ride on it, and then you can start this particular truck going along. And then what you see is that as the truck goes, you can see the two wheels or four wheels. I mean, in this case, there's a one line going along, and we just picked that one. And you can see a sort of a compression right under the, and then you see the tension, which is on the two sides of the tire. And you can see it's moving along here. And then you can do what we call a water flow, sort of a plot. You can see this is a distance, channel the distance versus time. So the truck is moving along here, which is going this way. And you'll see later on, the truck was coming back, and then you can see the signature of that particular one. But this one is 1 microstrain.
Professor, you have got 5 minutes.
Yes, thank you very much. Yes, you can start to have people running on that pavement. And this is, you can see the footstep, and you can see jump, 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 jump. And that is what we see. And that is going to 0.1 microstrain. You can walk, so you can walk, because you walk, your path is a little bit more smooth. So you can see along here how you're moving. You can have a bicycle. Bicycle will have a line like this, so you can see that. And again, this is like 0.1 microstrain. You can have a dog. So your dog is running over here. And then that's what it's moving. And you can see the footstep of the dog over here. And that is coming to what we call 0.02 microstrain, which is 20 nanostrain, much more sensitive than any vibrating wire strain gauge that we have. So there's a great opportunity to start using this kind of technology for geotechnical engineering. I'm not sure you want to know that vibrators or that kind of details, but there's an opportunity to get into that details. So these are sort of a little bit more difficult to see, but you do see the trace of this dog running, and it's coming to 10.01 microstrain. So in summary, we start to see an innovation in sensor and data analytics. It's exciting opportunities for geotechnical engineering to understand the real performance of our infrastructure during construction and operation. I showed you that distributed fiber optics can give you interesting data set that you probably haven't seen before, we haven't seen before. And that allows us, I hope by embedding the fiber, it can be an integral part of the construction package that you can use it for long-term proactive monitoring. So you can look at construction control by looking for the maintenance or actual performance, or resilient against hazard. If the earthquake happens or something nearby construction happens, you can protect because you have the fiber inside your infrastructure, and perhaps you can use it for reuse. And then the data-rich geotechnical engineering allows adoption of what we call whole life performance-based design, construction, maintenance, and reuse. And I see a lot of students are interested in this, and I see this as a rise of geodata analysis, which are our younger engineers. So I think the future is bright. We just launched the Center for Smart Infrastructure really to promote this for that kind of project that you have seen. So if you do have time to visit the area, please do so. And then I'm happy to show this around to you. Thank you very much for having. And if you have any questions, please email me. Thank you very much.
Thank you, Professor Soga, for a very interesting presentation. I think this is an eye-opener for most of the geotechnical engineering community. And how do you embrace ML, machine learning, and data analytics with geotechnical engineering is a question that most of us have. And I think you have rightly answered most of the questions. It's an important topic, but at the same time, the time is too short. Actually, it is not easy, and it's not easy to answer as well. So I just skip the questions because we have so many publications in this area, and tremendous work he has done. And there are more than 400 publications, a lot of work he has done. So my request would be to all the participants to visit his homepage. There are a lot of presentations by his group, actually. I mean, I found it very interesting. I request all of you to go through that. And I would like to thank Professor Soga for a very brilliant lecture. And I look forward. We invite you, because it is not in person, but India is a hospitable country. I request you to visit India and enjoy your hospitality, and we'll have we can give a lot of insights into various ways of working there. Thank you very much, Professor.
Thank you very much. Thank you very much for listening. I appreciate it very much.
Yeah, thank you so much. Yeah. So, Professor Muthukumar, shall I go to the next speaker? Is it okay?
Yes, sir, please. Please proceed. There is one question. Maybe time permits.
Okay. Yeah, you want to? Yeah. Okay. You have a question? Yeah. Please go ahead. Yeah.
No, sir. We already sort of time. We'll take it later if we get the time.
I know. I mean, I don't want to delay, Professor. It's already late here. Yes, so if you want to do it right now,
Please proceed to the next speaker, sir.
Okay. Thank you. So let me welcome the next speaker, Professor Dr. John Endicott. He's an executive director of AECOM and adjunct professor at Hong Kong University of Science and Technology. His topic would be on learnings in underground metro design and construction. He is an AECOM fellow and an executive director of AECOM's Geotechnical and Tunnel Business in Asia and Pacific region. He specializes in geotechnical engineering, and he has been working a lot in Southeast Asia and essentially based in Hong Kong. And he did considerable work in many committees and many regulatory bodies. And I don't want to, we can directly listen to him because he led a lot of vast experience in underground work. And, I think we can listen to him. That's the best way to, take advantage of his presentation. Thank you. I welcome Dr. John Endicott. Yeah.
Good morning, everybody, and thank you so much for inviting me to give this speech, this talk. And following behind our friend Kenichi Soga, this is quite a challenge. He's such an engaging speaker. I'm going to go off on a completely different line, which is to talk about things which go wrong during construction and the sort of lessons that we learn from them, because historically, engineers have learned from failures in the past, but hopefully we design for no failures. But nevertheless, for some reason or another, failures still occur. Fortunately, not very many of them. And this is typical of a failure next to a deep excavation. In this case, there was a washout by a broken water main, but the effect was quite disastrous. The main street in Hong Kong was shut down completely for a month before this could be repaired. So the consequences of failure are quite disastrous. And the reason for this failure was really very simple. If you can see here that there's steel sheet piling, which was not towed in because there was rock exposed at excavation level. And when the lower strut was removed, there was a mechanism. I think this is elementary structural analysis, but nevertheless, people on site remove struts and leave one strut behind when two are necessary. Now, this is my main topic, which is a classical failure, which many lessons were learned. And this is the collapse of the Nickel Highway, which is on the bottom left of the picture, because of a deep excavation for the subway system in Singapore. And it happened in 2004. And there was a massive inquiry, which lasted nearly a year, about 8 months in all, as to why it happened. And so many things happened, but I'll just pick up one or two of them. And this was the effect of the collapse. And you can see that there were 3 cranes on site. There's one crane here, another crane here, and another here. This mixer truck has dropped about 8 meters. But the 2 sides of the diaphragm wall have come together. The steel strutting has been pushed up into the air by this massive collapse. The volume of the collapse was about 50,000 cubic meters. And it was really quite devastating. There were 4 fatalities, and as one might expect, but I won't go into that story. I'll just talk about the engineering that was involved. The first sign of distress on site that led to the collapse was in February, which was 2 months before the failure. And you can see that this horizontal wailing should be horizontal, but it's distorted because this part of the strut has actually dropped. And you can see that capacity of something which is inclined is not going to be the same as the capacity of something which is horizontal and straight. Well, that was the first sign of an event. But later on, just before the failure, at the location of the failure, the same deformation happened. And you can see it was more than that this strut coming in from the right has deformed this flange, and the end plate is deformed. And someone has welded in a short piece of channel section in order to do a site repair, instead of making a proper connection, which would have had a gusset plate in here and a gusset plate in here. If you're familiar with structural steel, you know what I'm talking about. But as I said, there's so many things that were wrong with this site, so I'm a little short of time. And what was wrong with that repair was this is shown diagrammatically with the H section in the middle and the channel on the top. And it was said there was a piece of channel on the bottom, but I'm not sure whether there was or not. But when it's loaded, of course, it still sways. So that all that this repair did was to enhance the capacity, but it didn't enhance the capacity enough. And after the event, in the structures lab, this connection was modeled. It was assembled in the laboratory conditions with two pieces of channel and loaded until it distorted. Turn it on its side, you can see that it looks much the same. It's just a vertical arrangement in the structures laboratory. And this is the load and deflection curve, which shows that steel can be brittle due to this sway buckling phenomenon. Normally with steel, if it's constrained, it strains hardened. But in this case, you can see over here with my pointer, from load 0, it was quite elastic up to a point. And these were 3 or 4 different configurations of the junction. But the properly made junction I just showed you went all the way up here to about 4,200 kilonewtons. And then it sway buckled and it lost its capacity completely. So this is actually a very dangerous type of connection to make. It's got no reserve capacity. It's no plasticity, which is what one would normally associate. And this shows on the morning of the collapse, 2 such connections which already swayed, and the engineers on site were aware that this was a problem, and they went up into the site office because there were strain gauges on the struts which were being monitored on an hourly cycle, displayed on the computer in the office, site office. And as the engineer said, we checked the monitoring of strut force, and the strut forces were much less than the capacity of the struts, so there's no problem. So that was a sensible thing to do, to check the forces in the struts. And this site engineer, quite a young man, took a gang of workers down into the shaft, into the excavation, and tried to set about repairing the system. In fact, they were not able to repair it, and in the afternoon it collapsed. But what did he actually see? What he saw on the display, these are the readings for 9 levels of struts. And the last strut, 8 days before the collapse, had been installed, and as they excavated beneath that strut, of course, the force in it increased as would be expected, all the way up to here. And then for the last few days, it was fairly constant. And the strut above it, number 8, the force in that was slightly dropping as the reaction in number 9 increased. So the mechanism of load transfer was to be expected. But what was it that the site engineer had actually missed? And what he'd missed was that he didn't check what the design forces would be. And the design forces for these 9 rows of strut are shown plotted here in purple and pink color. And the actual measured forces were in black. And you can see that the bottom strut, the 9th one that he's talking about, that 4,200, the load there was far less than what it should have been. And if you look at overall, the sum total of all the forces in the strut, the design should have been 28,000 kilonewtons, and the actual measured was 19, which is 1/3. So if you think of a factor of safety of 1.5 on supporting the soil pressure with forces in the struts, then when you've got 2/3 of the design value, it means that you've got absolute equilibrium of 1, a factor of safety of 1 on the measured strut forces against the force in the wall. So this is obviously a precarious situation. And what the site engineer hadn't recognized was that the forces in the struts were a lot less than were predicted. And in those days, the stop work limit, the alert and alarm level limits were set according to the maximum force in the strut, because the alert levels and so on were aimed at safeguarding the force in the strut and the capacity of the strut. And the converse is that the strut is supporting the wall, and if you don't have enough force in the strut, then the walls will be moving too much. And in the event on the 20th of April, the walls gradually moved faster and faster until they collapsed. So this is a sign of imminent danger, and people should look and should apply minimum forces in struts in order to protect the wall. So the strut is monitored 2 ways: maximum force to protect the strut, minimum force to protect the wall. And that's what should have been done. But the site engineer was not alert to that because nobody had given him the design values. Now, when do these problems start on site? The struts were monitored with strain gauges that were stuck on them before the struts were installed. And in order to control deflections, the struts were preloaded. And on this diagram, you can see that the strut at the 9th level was supposed to be preloaded to 6,100 kilonewtons. And during excavation, depending on which analysis was being used, which is a derelict on this site, well, can I find it? You can see that the red line, it was predicted that the force in the strut should go up to a maximum of 9,991. And the other analysis was 8,700. But nevertheless, whichever analysis you use, because this was the matter that was discussed in the inquiry, that was the behavior. But in fact, what one measured was that the first reading immediately after lockoff, the preload, the load that was actually locked off in the anchor was down here. It's this small value, and it was still dropping down to this small value here. And then during the excavation, it increased a bit up to this value, and then it reached that value on the morning of the failure. And in fact, you can see that during the failure, the readings were still there, and it actually dropped down to there. That was the last reading, which was taken only about half an hour before the actual collapse. But these are way less than they should have been. And in fact, the retained load from pre-stress was only 20% of what was intended. And the maximum force that the connection could and the strutting could withstand was only 30% of what was actually required. So because that connection of the whaler was sway buckling, its capacity was far less than the design capacity and was far less than the capacity of the strut. And when the preload was applied, it's quite likely that that connection started to buckle. And the photograph that I showed you earlier on with the 2 struts with a buckled connection were only approximately 35% of the force. The photograph was taken at about this point of time. Now, nobody noticed this. If you're applying pre-stress, then the pre-stress is expected you normally apply with a jack just a few percentage more than the design preload. So when you lock off and the wedges draw in, there's perhaps 5% loss. And this is carefully monitored, say in post-tensioned bridge decks and so on. And people make sure and study these things very carefully. But it seemed to me that on this side, nobody had actually bothered to look at the monitoring of the forces in the struts that were induced by the preload, because after lockoff, there should have been about 6,000 kilonewtons measured in each strut, and it clearly wasn't happening. So if people had actually looked at this and monitored the forces in the strut during and after the pre-stressing, or during the, 5th to the 21st, 16 days, a fortnight, during which time the locked-in stresses in the struts were far less than they should have been, someone should have realized there was a problem and should have investigated. And this, it's even worse because in March, the same thing happened when the strut at level 8 was preloaded. You can see the same pattern here. I don't need to repeat it particularly, but you can see that there was a required locked-in preload of 7,400, expected to rise to above 8,000 at the time when the 9th strut was about to be installed and preloaded, and then it would drop. And you can see from the trace at the bottom that the retained preload was only about 20% of the required preload, and the maximum that was achieved at that stage was 40%. Although you can notice that on the day of the collapse, if I can pick it up, the arrow doesn't show very well. Whoops. That it's lost on the white background. That at the end of the day, on the 21st, on the 20th, going towards the 21st, as the load in strat level 9 in the previous plot was dropping, it was transferring its load into this connection, which went up so far and then collapsed. So just to sum up, immediately after lock-off, there was a loss of pre-stress, and this was apparent for the 7th layer, the 8th level, and the 9th level, which was 9 weeks before the collapse. So if people have looked at the monitoring that had been installed, understood it intelligently, they could have anticipated that there was something really seriously wrong with the strutting, the steelwork of the strutting on this project. Now let me move on to the next lesson that's learned. There were many experts called into the inquiry because there were so many parties involved. There was the main contractor, there's a two subcontractors, there's a permanent works designer, temporary works designer, checker, insurers. And each of these persons was represented at the inquiry with and put forward experts who gave opinions that might be useful to guide the inquiry, the court of inquiry. And 3 experts reported that they had analyzed the collapse using finite element models, and they'd said that the model predicts overall failure due to base heave. And base heave is when the soil at the bottom of the excavation is so soft that it rises as the embedded section of the wall beneath excavation level is pushing forward and trying to develop passive pressure. Now, this site location was a reclamation which had very, very thick clay deposit, marine clay, and sand fill on top of it. In fact, there was evidence from piezometers installed before excavation that there was still some residual positive pore pressures from the reclamation, and that the clay wasn't fully consolidated. So the clay was relatively soft at formation level. It had a cohesion of about 20 kPa, which is rather like toothpaste, a little bit firmer than toothpaste, not much firmer. So it was quite a possible mechanism of failure could be that the pressure from these 2 diaphragm walls pushing towards each other would cause the base to heave. Now, in the diaphragm walls and in the soil just behind the diaphragm walls, it just happened that the location of the failure, in the middle of the location of the failure, there was an instrumented cross-section with inclinometers on either side of the excavation. And these inclinometers, if you don't know, they're tubes which either cast in the diaphragm wall panel or bore down into the soil just behind it. And by using a torpedo, you measure the lateral displacement, or therefore the deflected profile. And this is a series of deflected profiles from the 19th of February to the 20th of April, at which point the wall collapsed. And you can see the maximum deflection is unusually 400 millimeters, but this was on midday when the wall was in the process of deteriorating towards the collapse. But if you look at the bottom where the blue arrow points, which is close to the bottom of the diaphragm wall panel, you'll see that there's been no forward movement of the bottom of the diaphragm wall, which means that diaphragm wall was bending quite severely with a maximum bending just below the black line, but the bottom of the toe of the wall was not kicking in. Now, in order, if the soil in front of the wall was rising and the wall was kicking inwards due to a base heave, you'd have seen the bottom of that wall would have moved in excess of the top. So the experts were wrong. And what surprised me was these experts were quite eminent people, and they're supposedly specialists in deep excavation, and inclinometers have been in use for many, many years, and they're standard measures to forms of instrumentation. And an expert who was trying to work out the mechanism of failure should have been given access to such instrumentation like this, which shows the bent deflection of the wall and whether or not the toe kicked in. And if they weren't given that instrumentation, they should have asked for it. Incidentally, if you're wondering why the profile is so wiggly like this is because extensometer tubes are slotted to allow for the deflection. And those that are in soil, the slots move, and this gives a false reading along the way. So you can't be sure that the maximum bending moment down at the low level is actually the maximum down at this level. Because of these, that happens to be where there's a slotted case. But never mind, that's just a point of detail. Inclinometers that are cast in a diaphragm wall don't need to have, don't use those slots. They remain the same length, and therefore you get very smooth profiles. Now, the next point that the further information one can get from inclinometers, as I've already mentioned, is how much the wall has been bent. And you can see this visibly. There's a displacement of 400 millimeters or thereabouts over a length of so many tens of meters. And if you think about elastic beam theory, the bending moment is the section modulus times the coefficient of Young's modulus, EI, divided by the radius. In other words, the smaller the radius, the bigger the bending moment, and the larger the radius, the smaller bending moment. So if this was an elastic beam and you saw the radius of the curvature of the wall, you'd be able to work out the bending moment directly. But of course, concrete is not elastic. Concrete cracks on the tensile strength. The concrete and the steel is elastic up to a point, and then until the concrete crushes or until the steel yields. And there are ways of calculating the bending moment versus curvature for reinforced concrete sections. I won't go through all of it. I'll just copy it to you. You can find it in most reinforced concrete codes or attached to them. And you end up with curves something like this, depending on the cross section, that from the initial load, it's linear elastic, and then the concrete cracks, and then the steel yields. But what's important is that the radius of curvature of about 100 to 200 is when the steel starts to yield with an under-reinforced concrete section. And you can see that at the right-hand end of the graph, you have a radius of 20 meters, and the steel is still yielding. It hasn't actually failed yet. So that's those are the sort of parameters to look at. And if you look at the deflected profile, and if you try to fit a curve of 200 meters radius, which is roughly the onset of yield in the steel, you see that was matched approximately according to the curve, and on the date of the 3rd of April, which is 18 days before the date of the collapse. So again, if people had understood these large deflections and the radius of curvature, they'd have been able to see that the reinforced concrete section of the diaphragm wall was already yielding 18 days before the collapse. And people should not be using diaphragm walls when the steel reinforcement is yielding. There should be a factor of safety against that. And when I go back, yeah, no, I didn't add any comment further on it. Now, can one actually put this to good use? Because the observational technique is to monitor it to performance, analyze the performance, check out what's actually happening, and then forecast what's going to happen next. So back analysis of a deflected form is quite a proper technique to work out what's actually happening. Instead of just picking the maximum radius that I showed in the previous slide, you can do a back analysis to where it goes. Now, in the case of this project, they had AAA limits, and the first one was the alert, and then there's the action, and there's the alarm limit. And the alarm limit is when you're supposed to stop work. And the alarm limit was set on this diaphragm wall at 160 millimeters. And the wall reached 159 millimeters on the 23rd of February. The project they had to stop work. They had to check what the conditions were, revise the analysis if they wanted to, which they did. They said the wall was okay, and they reset the alarm limit to 300 millimeters by doing a back analysis, working out revised soil parameters, and then using those soil parameters to predict what would happen in the future as they could carry on work. So they resumed work, and by the 3rd of April, the wall had hit the 300 millimeter limit, and they stopped and did a second back analysis. And in fact, there was toing and froing between the client and the contractor and the temporary works designer, and they continued to work because they were due to hand over this site at the end of April. And the project management team was saying, no, you must finish this on time because you have to hand over to the track work contractor, and he's very litigious. They'll put in a massive claim for delay. So the project continued, having reached a stop work limit without the stop work limit having been lifted, but it was just being ignored, which is something else which you should learn. You should never ignore a stop work limit. Anyway, if we look at the back analyses, this is the first back analysis shown as the solid line, and the inclinometer data has been smoothed out because this was a soil inclinometer, but the maximum deflection of 159 was matched by the back analysis at 161. So at that point, the back analysis fitted the curve. But if you go down to the depth, which is actually elevation, say 70, you can see that the dotted line with triangles has got only half the deflection of the back analysis. So the back analysis wasn't very good down at that level, which means if you also look at the radius of curvature where the arrows are, you can see the actual radius of curvature was about 1/3 of the back analysis, which means that the actual bending in the wall was 3 times distressed compared to the back analysis. The back analysis said the wall is safe, it's still within the elastic limit, but the real wall had actually bent 3 times as much, and nobody had matched that. And likewise, on the second back analysis, the back analysis was the dark line shown on here. And there are 2 inclinometers facing each other. And I showed you the one on the left before, because that's the one that's in soil. The one on the right was on the opposite side of the excavation in the wall. The site was the soil strata were slightly asymmetric, so the wall on the right-hand side didn't move as much as the rest. But by doing a symmetrical back analysis, considering half the section, of course, the back analysis didn't fit either wall, and you can see the radius of curvature was far bigger, the curve was far gentler than the deflected wall on either side of the profile. So what was learned from this? The client appointed independent checkers for temporary works. They commissioned re-examination of all temporary works that were underway and revised design principles for temporary retaining walls. And they included measures of risk reduction, so there should be no overstress for design of temporary walls. I think this is now generally the case for deep temporary walls like this. There should be independent checkers. There should be independent monitoring of the instruments, because it came to light that some of the instruments were faulty and nobody bothered to recognize that or to correct them. Also, the use of a computer program Plaxis should be checked for both drained and undrained conditions. I haven't explained that, but it's another story. And the supervisor should be independent and not employed by the client or by the designer or any other interested party. And since then, which is 2004 to 2021, 17 years, there have been no subsequent major collapses in Singapore. And these rules are still in force today. So were the lessons learned? Well, I've given this lecture, I don't know, dozens of times. Certainly in Singapore, people are not doing what was done at the time because the authority having jurisdiction has required that things are done more carefully, more properly. But 4 years later, after the collapse of Singapore, so this is 2008, I was visiting a site in a nearby city in Southeast Asia with a 30-meter deep excavation, so that's the same. 10 levels of struts, that's the same. There's splays at the end of the struts going on to horizontal wailing beams, which are the same, at least in this part of the site. Forget about the bit on the right, which has got a ping pile and lacking the bit on the left, which is anchored. But in this corner of the site, there's a substantial recess in a massive excavation, which has got very similar steel structural arrangement to what happened in Nickel Highway. And if you look at their engineering drawing, if you see the strut coming in from the right-hand side, bolted to the whaler, and the whaler has an H section on its edge, and it's supported by a bracket. And there's a stiffener on the top. And instead of being a channel, it's an angle, which is like half of a channel, and there's no stiffener on the bottom. So this is a very similar detail, but worse than the one which collapsed in Singapore. So this lesson wasn't learned because the designer for this job was represented at the inquiry at a senior level from the same company, where that detail that I explained to you right at the beginning was examined by several experts. And this is what happened a few days after, the previous photograph. And I can't say that that connection detail was actually a cause of this failure or a contributory part of the failure. But nevertheless, that sort of detail should not be used. You know, it costs a lot of time and money to an engineer.
Sorry to interrupt, sir.
Yeah, I'm about to stop. Thank you. That's the end. There you go.
Yeah, thank you very much. I think it was a brilliant presentation. We have time for questions. Is it Professor Kumar? Is it right? We have a couple questions for time for one or two questions, right?
One or two questions we can allow, sir.
Yeah.
From chat box if you are getting.
I don't find, I think.
No questions in the chat box. Maybe we can, any panel members in the panel, you can directly ask the question. Yeah. You can unmute, you can ask the question, panel. Maybe one or two quick questions.
Just I have a question. In fact, is it the typical issue with all the soft soil problems or in excavations and soft soils, or like, I mean, do you have any construction guidelines now? Is it because of these failures? Just wanted to know.
So I didn't hear that very well. Instruction.
Do you have any construction guidelines on placement of some of this thing and the instrumentation? Do you have any guidelines for the local government offices?
Well, the guidelines that were promulgated in both Hong Kong and Singapore, where I work mostly, and I've worked in other countries as well, are normally concerned with the safety of the works and the instrumentation, the amount of instrumentation. It's not so much checked so much as it's up to the designers to make sure that there's enough there. And there's a culture in both Hong Kong and Singapore of putting in a lot of instrumentation, and there was in 2004 when this collapse occurred. My concern was that people were not taking notice of it and interpreting it properly. And I think that was the big lesson that's learned. And certainly I can see now that the instrumentation engineers are now much more careful in making sure the instruments are working properly. And the site engineers are then fully briefed as to what the design is about and what the alert levels actually mean. But having said that, and the other benefit is that a lot of the instrumentation is now available through the internet. So you can look it up on your iPhone or on a computer and you can see real-time monitoring. So they're a lot better facilities than they were, as I said, in 17 years ago. In order to see what the forces in the strut were, the engineer had to go back into the site office and look it up. Now you can just call it up on your iPhone and you can see what it is live. And if you want to, you can plot movement against force in the strut and so on. These facilities are much better than they were in those days.
Yeah, so thank you.
You're very welcome.
Yeah, so any more questions? Of course, there is a question. I think you have given a present, the material is available with the organizers, because there was a question on, please explain once again the connection problem, but I think it may not be possible. But if it's available in your lecture material, it should be fine.
Right. Mm-hmm.
So I'd like to thank you for, on behalf of the organizers, for a wonderful lecture. I think it is one of the most studied failure cases, and I think your explanations are so lucid, and I think we need that level of instrumentation. Particularly, it goes well with the lecture of Professor Kenichi Soga, who was talking about instrumentation so much. Thank you so much. Yeah.
You're very welcome. Thank you for inviting me. It's a pleasure.
Thank you. Thank you. So I now we go to the next speaker, next keynote speaker. It is Dr. Sri Ravindra Kashinath Ganekar. He is a retired Chief General Manager, Geotechnical Section, Institute of Engineering and Ocean Technology, ONGC. He would be talking on Cptu applications in offshore soil investigations, equipment deployment, and data interpretation. I should say that he did his postgraduate degree from Roorkee, and he has been working with the ONGC for a very long time. He has a number of publications. He has been a member of many technical bodies, and he is also a member of the TC 209 of the ISSMG and offshore geotechnics. He edited a book on offshore geotechnics in '92, and more than that, he's a good friend of mine. Welcome, Sri Ravindra Kashinath Ganekar.
Thank you, Professor Babu. And good afternoon to all, and welcome to is it visible?
Yeah.
So good afternoon to all, and welcome to my presentation, which is titled Cptu Application in Offshore Soil Investigations.
Sir, your PPT is not visible.
No?
Yeah, please open your PPT.
Is it visible now?
No, not yet, sir.
Not yet, not yet.
Not yet.
Please use that share screen, green button. Share screen.
Okay, sorry.
Yeah. Yes, you can open your PPT.
Yeah. Sorry about that.
Yeah.
Fine.
Yeah, now it is fine, sir.
Yeah. One of the most important components in offshore geotechnical investigations. So I chose this topic because unlike in onshore soil investigations, CPT is an essential part of any offshore soil investigations due to its versatility. And it appears to me that the advantages of CPT or CPTU piezo cone in onshore soil investigation is not fully appreciated. Another objective is to present Indian offshore experience with the piezo cone penetration testing as far as possible with a limited time. So the content of my presentation would be introduction, deployment, interpretation, additional sensors, and direct application for pile design. Coming to introduction, as we know that in-situ testing is to augment information from sampling and laboratory testing, and it involves insertion of a probe that measures the soil reaction, which can be interpreted in terms of geotechnical parameters. Large number of in-situ tests are in vogue in onshore, but only a few tests are commonly used offshore. One is the piezo cone penetration testing, CPT or CPTU, and field vein shear test, and full flow penetrometers like T-bar or ball penetrometer. The most versatile and popular in-situ test in offshore investigations is the CPTU or the piezo cone penetration testing, which will be the focus of this presentation. Actually, in offshore, the CPT was adopted from the onshore practice, and the first deployment in offshore took place in 1972. Many aspects are similar to a large extent in onshore and offshore, like the probe, the data processing, and the interpretation. However, in offshore, there are special challenges for the use of CPT or CPTU. One is the need for special working platforms. Since we are working underwater, we need special platforms like jackups, vessels, or the seafloor-based systems. And since the deployment is underwater, there are special requirements for deployment equipments and techniques. Generally, the investigation is much deeper in offshore, like starting ranging from 5 meters to 200 meters below sea floor. And because of the harsh environment offshore, it is very essential that the safe and efficient handling of equipment is done. The basic CPT, as we know, it measures the resistance of soil on cone, called cone resistance, friction in terms of stress on the cylindrical sleeve behind the cone, called sleeve friction, and also inclination to correct the depth and check that deviation is not too much. It requires a pushing system, internal instrumentation, and data acquisition system. Piezo cone penetration testing is an improvement over the basic CPT, where pore pressure generated due to the penetration is also measured. We have a porous filter element made of plastic, ceramic, or metal on either cone face, behind the cone, or behind the sleeve. This most commonly used in-situ test is this CPTU with the standardized filter location behind the cone, that is called the U2 location. Sometimes other locations of filter also are used. Quality and reliability of the CPTU data is generally very reliable, but some issues must be considered, like periodic calibration of sensors, proper maintenance, corrections on measured raw data, which is very important, and correct test procedures. The standards which are applicable and which are used in offshore penetration testing is the ISO 22476-1, ISO 19918, marine soil investigation, and ASTM D5778, Part 12, 2020. Coming to the deployment, There are basically two deployments modes in offshore. One is the seafloor or non-drilling mode, which involves pushing the Cptu equipment from the seafloor continuously till refusal or to a predetermined or predefined depth below seafloor. The second mode of deployment is down the hole or drilling mode, which involves drilling a borehole and pushing the bone penetrometers hydraulically into the soil at the bottom of borehole. Such deployment can also alternate with sampling of the soil. Very recently, hybrid type of deployment systems have also been developed and used, which employ remotely operated seafloor-based drilling rigs and can do sampling and perform Cptu to large depths below seafloor, similar to traditional down-the-hole systems. Now, coming to seafloor mode or non-drilling mode, you can see there is a seabed frame, and this air station shows what is called a wheel drive system, which continuously pushes the cone up to generally about 40 to 50 meters it can go. This is truly continuous test, which enhances the quality, increases efficiency, but requires check on inclination of the probe. Now the second mode is down the hole mode or drilling mode. This is a common mode of deployment for deeper investigations. And sampling and Cptu done through open bit drill strings. So you can see here, generally first a sampling is done, then the sample is taken out and the disturbed soil is drilled through. Now the cone penetration is done, Cpt stroke, then it is removed, and again this disturbed soil is drilled through, and so on and so forth. Cpt stroke is generally typically 3 meters. This is an example of the Cpt profile. You can see that various different kinds of soils are how they react to the penetration of the cone, and these are reflected in the measured parameters like cone resistance, leaf friction, and pore water pressure generated. It is essential to have corrections on raw data, and especially the cone resistance. Actually, due to internal geometry of the Cptu equipment, ambient pore pressure acts on the shoulder area behind the cone and at the ends of the friction sleeve, as shown in this illustration. Generally, there is no filter element behind the sleeve. So the correction to the skin friction or sleeve friction is generally not done. But it is important that we do the correction for the cone. And it shows the correction which is to be applied. And since different makes of cone have different area ratio, so which can range from 0.59 to 0.8. And this correction has been applied to offshore since 1983. There is another correction because for true comparison, correction for seabed reference, which is needed for down the hole test as the sensors are zeroed at the depth. So all test records are needed to be brought to the same reference value, that is seafloor, by applying necessary correction. Measurement of cone parameter is affected by the following commonly observed problems. There is soil disturbance due to drilling. Because of the movement of the ship, many times the drill bit hits the undisturbed soil and disturbs it. So there is a need for proper heave compensation installed on the vessel and the need for controlled drilling. Improper filter saturation. Actually, there are standard proper saturation procedure which need to be followed. Otherwise, the response is very sluggish initially. Now, because of the instrumentation problems, change in zero reading also takes place, which needs to be checked continuously throughout the test. There's another problem is that sinking of seafloor rig in soft seafloor. So that causes does not allow the surface soils to be properly characterized, which is very important for the submarine pipelines. So there are some special onboard measures which are needed, like use of skirts for seabed frame or increased base area or the reduced weight. Many times, periodic maintenance or inspection for wear and tear are also neglected. So now here is an example of the soil disturbance due to drilling. You can see the initial part of the Cptu profile, bone resistance. The response is very sluggish. And the similar thing is with the pore pressure. However, if you see the right side of the right side picture, it is a far better measurements. These two are the examples of the poor filter saturation. On the left-hand picture, you can see towards the left, the very poor saturation, slightly better saturation, and what you should get actually. And on the right illustration, it is an example from Western Indian offshore. The black line shows the bad saturation, while the blue line shows improved saturation. And as I said that there are different makes of cones available, and so the corrections are required. And you can see that here that after the corrections, generally the repeatability of cone resistance measurements is extremely good. So it shows the four different cones. And same thing is with the pore pressure also. It's very repeatable. While if you see the sleeve friction, because the corrections have not been generally made, you can see how much difference is there in the measured sleeve friction using different cones. Now, coming to the interpretation. Actually, overburden stress and depth influence the measured Cptu parameter. Hence, the normalization of measured parameter for use in interpretation is very much desirable. Commonly used Cptu derived parameters include normalized cone resistance, normalized skin friction, normalized pore pressure parameters BQ, friction ratio FRF, and the soil behavior type index IC. So I will have reason to discuss IC more later on. But I can say that the soil classification on almost all required design parameters can be interpreted using the above Cptu derived parameters from empirical correlations. So I'll be discussing the interpretation of soil classification, in situ state of stress and stress history, strength parameters, deformation characteristics, and flow and consolidation characteristics. We'll also give Indian experience wherever possible. As we saw that different soils respond to the cone penetration differently. So here is general trend of soil type response to penetration. You can see that For example, soft to firm clay, the cone resistance is low, sleeve friction low to medium, and pore pressure is always positive. Similarly, for dense sand, the cone resistance is very high, sleeve friction is medium to high, and pore pressure may be ambient or the somewhat negative. And this has allowed researchers to come out with what is called a soil behavior type classification. But our experience shows that the grain size based classification and the SBT classification both match quite well. A large number of schemes have been proposed in literature, but the most commonly used classification systems are by Robertson and Wright, which I will be discussing in some detail. Now, Robertson 1990 gave two charts, one between the normalized friction ratio and the normalized cone resistance, and the pore pressure parameter BQ and the normalized cone resistance, and defined various zones on the chart which show the soil type. However, one disadvantage of this is that the stratigraphy or the sequence of layers cannot be discerned very easily. So Robertson and Wright in 1998 came out with what is called the Soil Behavior Type Index, IC, which is a function of normalized cone resistance and normalized friction. And they gave the range of ICs for various kinds of soil, like gravelly sand to sand, which is IC is less than 1.31. For clays and silty clays, the IC is between 2.95 and 3.6. Now, if we plot this soil behavior type index against the depth, then it becomes very easy to discern the soil profile and the layering and stratigraphy. This is an example from Western Indian offshore. You can see that up to about 12 meters, the soil is clay. Then we have from say around 15 meters to about 25 meters, it's a sand layer. Again, some mixed profile like some sand seams and the clay. Again, the clay, and then again a mixed, very mixed kind of soil. So coming to Cptu interpretation in terms of engineering parameters. So a number of theories have been used for interpretation of Cptu results, like limit equilibrium, elasticity, plasticity, or cavity expansion, etc. And it must, however, be recognized that all theories make some simplifying assumptions, and their recommendations need to be verified by actual field experience. However, they do serve a very important purpose, that they give the direction to develop the empirical correlation, which are naturally preferred by practicing engineers. So in this presentation, focus will be on empirical correlations only. Coming to in situ state of stress and stress history, I'll be discussing soil unit weight, stress history for clays like over-consolidation ratio, in situ horizontal effective stress, K0, and relative density, dr, for sands. In situ state of stress, the unit weight of total unit weight of soils. A number of proposals based on the regional experience have been given by researchers. When we studied it for our Western Indian offshore, we found that the relation proposed by Robertson and Cabal, it gives, it predicts reasonably for depths less than 30 meters. While for deeper depths, Main and Puken 2013 relations predicts quite well. Now, the most commonly used relationship for over-consolidation ratio is by Glavi and Mann, which is the OCR is a linear function of normalized cone resistance. The factor K ranges from 0.2 to 0.5 and higher for aged heavily over-consolidated clays. And then the average value of 0.33 is generally applied for preliminary estimations. Main also proposed a similar expression for pre-consolidation stress for all kinds of soils and linked it to the soil behavior type index IC, as shown in the right side picture. Now, coefficient of earth pressure at rest. There are two ways rather, it is generally interpreted from the OCR derived from the Cptu measurement, restricted to mechanically over-consolidated clays. A number of correlations have been proposed, and one example where NGI and our institute was involved was derived based on a high-quality database containing data for clays having range of OCR from 1 to 100. And it was a good correlation, has good strength, and which is shown here. Recently, Orsted or the previously Dong Energy had a project. Unfortunately, the data is presently confidential. I was to some extent involved with that project, and we found that good correlation is shown with derived parameters from simultaneous multiple core pressure measurements, like cone face, behind the cone, and behind the friction sleeve. Now, coming to relative density. It is basically based on all the calibration chamber testing. A number of proposals have been given by researchers. An example is by Jamilkowski et al., 2003, for young fine to medium normally consolidated siliceous clays. And it's shown, the chart is shown here. A similar proposal they also proposed for the combined normally consolidated, non-over consolidated siliceous sands. Now coming to strength parameters. One of the most important parameters is the undrained shear strength, SU for clays. Then we have remolded shear strength or sensitivity and the friction angle for sands. So coming to the undrained shear strength, as we know that undrained shear strength is not a unique property of the soil. It depends on the mode of failure, soil anisotropy, strain rate, and stress history, and also the sample quality on which the testing has been done. So it is important that the interpretation of Cptu parameter in terms of undrained shear strength should specifically mention which undrained shear strength is being referred to as reference value. So there are empirical correlation based on the forms proposed by theoretical solution. And there are three ways of interpreting SU from the cone parameters. SU estimation using net cone resistance, as we will see. SU estimation using effective cone resistance, and SU estimation using excess pore pressure. So SU estimation using net cone resistance. Net cone resistance is nothing but the corrected cone resistance reduced by the total overburden pressure. And the NKT factor is the empirical cone factor. SU estimation using excess pore pressure. Now, again, you can see the delta U is actually the difference between pore pressure measured behind the cone and the ambient pore pressure of the equilibrium hydrostatic pore pressure. This is especially used when the soils are very soft, and it gives good results in that. SU estimation using effective cone resistance. This is not normally used in offshore practice. Only the first two are used in offshore practice. Now, here we can see how the cone factors vary. This is only an example from Brazilian marine clays. And you can see how much difference or area-wise NKT in area-wise NKT factors. And it is hence very important to develop regional correlation. Our experience in Western Indian offshore clays shows that the NKT factor applicable is 15 to 20. And for Eastern Indian offshore clays, especially the deep water clays, the NKT factor is from 12 to 16. Here, the reference tank is the UU triaxial test. Coming to remote shear strength or the sensitivity, the measured sleeve friction value represents the remote shear strength, and this has been recognized that by researchers. And Ramsey recommended that 2/3 of the measured sleeve friction should be used as the remote strength. However, regional correlations are required. There are other proposed expression also for sensitivities. Now, considering the problem with the sleeve friction measurement, the expressions are used only if confirmed by local correlation. We also tried to develop a correlation for Western Indian offshore clays for remote shear strength as a function of sleeve friction. Now, friction angle for sands. There are three ways of deriving friction angle. One is the indirect method, that is using relative density from Cptu and use of proposed charts like Anderson and Chetney shown on the right side top. Or we can also reconstitute sand samples in laboratory to the relative density interpreted from Cptu and carry out triaxial tests. There are some direct methods also, like the chart proposed by Jamilkowski based on Bolton's 1986 theory for silica, quartz, and calcareous sand. One example is shown on the right side bottom. Main also proposed a chart based on field and lab data, which is shown in the next slide, this slide. So it is recommended to estimate the value of the friction angle from various methods and use the value that is most conservative for the design problem at hand. Now coming to deformation parameters, I'll be only discussing the maximum shear modulus. The table opposite top shows that various correlations for Gmax with cone resistance proposed by many researchers, and the bottom figure shows the correlation of Gmax with corrected cone resistance for Eastern Indian deep water offshore case, as per our experience. Correlations for constraint modulus, so Young's modulus also exist, but are not very strong, so are not discussed yet. Coming to flow characteristics.
Excuse me, Mr. Ganekar, sir. You got only 5 minutes left, sir.
Yes, I'll try to complete it before that.
Yeah, I know, it's a request, sir. That's all.
Yeah. So, using the Cptu, what a test can be conducted like pore pressure, which is called pore pressure dissipation test. Penetration is stopped at a desired depth, and decay of generated pore pressure is recorded for a time depending upon the parameters to be derived and percentage dissipation to be achieved. The parameters interpreted are horizontal coefficient of consolidation, horizontal permeability, and in situ equilibrium pore pressure. These can be derived. Use of standard procedure for obtaining the required parameter. If vertical coefficient of consolidation or permeability is required. We generally use published anisotropy ratios applicable for the type of clay under consideration. An example is shown for permeability in the table. This is on the left side is an example of pore pressure distribution test result from near shore Indonesia at 53.9 meter depth. Now, there are some recommendations to go about interpretation of the engineering parameters from Cptu. Good quality sampling and lab testing is essential, but Cptu is also a necessary complementary test. For preliminary or early estimation of parameters when lab test results are not available, as a check on testing results, and for integration of data to prepare a regional or geological model and verify existing Cptu empirical correlation. With experience, generally the correlations are updated for a given area. Now, good correlations exist for soil unit weight, OCR, SU, Gmax, and CH, and relative density. Preliminary estimate can also be made for K0, SUR, sensitivity, and KH. Now, coming to the next section, additional sensors. Many additional sensors have been used along with the Cptu to augment the information gathered. Some of them are listed below. A measurement of shear wave velocity, what is called the seismic teaser cone or SCPTU. This is more frequently used compared to other additional sensors. And there are other types, additional sensors, like for measurement of in situ temperature, in situ density, in situ horizontal stress, acoustic noise for soil classification, measurement of permeability, which is called flow cone, measurement of electrical resistivity cone, even photographic recording of pore fluid or soil. It is called vision cone. The last two have also important environmental applications. Now coming to the direct application, considering similarity between shape, installation, deployment of CPT and pile, a number of CPT-based pile design methods in sands have been proposed. Here are the four listed: ICP, NGI, FUGRO, and UWA. The problem is that each method predicts differently, and no resistance factors have been recommended for the methods. As shown, you can see that on the right-hand side for axial and tension and compression capacity. Two GIPs were taken up by NGI to address these issues, where our institute, IoT, also participated. And the outcome of GIPs was based on a world-class pile load test database, established procedure for reliability-based analysis.
Sir, excuse me, only one more minute left, sir.
Yeah. I'm just finished.
Sorry, sir, extremely sorry.
For more details, you can refer to the keynote paper by Nadeem et al. In ISFOG 2020. Now coming to conclusion, Cptu is the most versatile in situ test and an essential component of all offshore soil investigation. Most of the required soil design parameters can be reasonably obtained using empirical correlation with Cptu parameters. Cptu results can also be used directly for design, pile design. Proper use of equipment maintenance, calibration, etc. are prerequisite. It is, however, cautioned that it is no substitute for sampling and laboratory testing, but is an important complementary test. It is strongly recommended that wherever possible, regional correlations be developed. Additional sensors can also be included in the Cptu equipment for increased versatility, and it is recommended to use Cptu tests more commonly in onshore soil investigation in India to take advantage of its versatility. Thank you.
Thank you very much, Ravindra, for a very nice presentation. Well, I have one question maybe, or I'm not sure. I think, what do you say, Professor Muthukumaran? What is your, I think?
You're already short of time.
Yeah.
No question from the chat box. Maybe we can have one quick question from the panel.
Yeah, maybe Balakumar, you want to say something, or we want to hand over the session to them, or whatever you
only
think
a brief
appropriate.
summary. It's only a very brief summary. I wanted to give, that's all, nothing more than that. Just 2 minutes time. See, all the 3 lectures were highly informative, and a lot of lessons which we have learned by the 3 lectures. The lecture presented by Professor Soga definitely showed a lot of improvements on the measuring systems and how to go about instrumenting and measuring the performance. Particularly, it is very useful in the case of pile foundation and pile draft, where the installation method has got a lot of influence on the pile behavior. The second lecture by Professor Endicott really reminded me of a golden saying, what 1,000 successes cannot teach, 1 failure will teach. It was a brilliant lecture, the way he has presented, and the forensic study that has been done in depth, and then how to come to the grassroots of the cause of the failure was really phenomenal. We learned a lot of things out of this lecture. We have to personally thank Professor Endicott for that. And the lecture by Professor Mr. Ganekar sir was really very impressive in the sense that how the point penetration test can be used in offshore geotechnics. But if it can be used so effectively in offshore geotechnics, it can be used as well in the onshore also. And a lot of interpretation and parameters, how to come out of it, which is very much interesting. And I think we'll have to give, presently, the more importance is on the field-based tests, not the laboratory tests. We need a more of a field-oriented test so that laboratory tests only will be confirming the field data which we are getting. And it helps us to do post-installation analysis or during the analysis, particularly in deformation, excavations, and pile draft and things like that. In short, all the 3 lectures were very brilliant and highly informative. And let me express my very sincere gratitude to the organizing committee and Professor Muthukumaran and the chairman of the session, Professor Shivrat Babu, for having allowed me to summarize the whole session. Thanks a lot, sir. Thank you very much for all. Thank you very much.
Thank you very much.
Thank you very much.
Yeah.
Thank you, sir. On
Thanks a
behalf
lot.
of the organizing committee, I thank the chair and co-chair for conducting this session very nicely. With that, we have come to the end of the session 1. So we'll break for lunch. We'll meet at 2:50 with technical parallel session 1. We have planned 5 calls, EEE RD, theme number 1, soil behavior and characterization of materials. A2 hall, theme number 2, geotechnical, geological, and geophysical investigation. A11 hall, theme number 3, foundation engineering. A12, theme number 4, ground improvement techniques. And A13 hall, theme number 7, earth retaining structures, dams, and embankment. Please rejoin with respect to your corresponding area of interest in these themes, and please come back by 2:50. Thank you all. Thanks, Ananda.
Thank you very much, Dr. Muthukumaran. Thanks a lot.